Hi, I'm Mark from the uTasker project. Today I've got an embedded artist board with its OEM module with the 1062 on it. Now I've already made several videos explaining how the uTasker bootloader essentially works and also how to build it with different IDEs. And this video is not really intended just to repeat that. What it's going to do is going to use this board just as a demonstration, which means that also embedded artist module users know that they can use the uTasker project immediately. So what I'm going to show you is how to precisely validate the security operation, which is useful not only for code reviews but also for peer reviews. Here I've used MCU boot utility and its eFuse operation utility to scan in the fuses. Presently, these are all default fuses, which means that in the software general purpose 2 area, we have zeros and they're not protected. Later we'll see that the lock register will change when we protect them, and then they are no longer readable. So now I'm using the same utility to program the bootloader and a uTasker application. Here I have a complete image prepared, and now I program it. So now I've got the board loaded with the uTasker bootloader and a uTasker application. So let's see what happens when we boot it up. Here we have a terminal emulator connected. Now I'm going to reset the board. So here we can see that the board is booted up. If I go to the administration menu, we have various useful commands. For example, the eFuse command. Now, the eFuse command also gives us a listing of the eFuses which we'd seen before. What happened is that when the bootloader started, it programmed a key into the software general purpose location, and also it protected this key. Here we can see some protection keys which have been set in addition, and the effect is that we can no longer read back the secret key. This secret key is a random number which is generated by the true random number generator, saved to this location, which can never be changed again. Since we cannot view it and we don't know what it is, nobody knows which keys are being used by this board. In addition, the key is unique to this board too. What I'm going to do now is reset the board again with a reset command. And after it's started up, we note that the flex RAM has been set up to have 2 code banks. That's enough to fit the code which the application is running into the internal instruction memory, and 14 data banks. Our stack pointer is at the top of this memory here. Now if I move into the input-output menu, which allows me to look at memory, and if I look at these 4 long words, I'm going to find something quite interesting. These are the keys which have been programmed by the bootloader. Now I'm going to make a note of these keys because we're going to use them later. Normally nobody would have access to these keys, as I'll show you by doing a power cycle of the board. Again, I'm going to check the keys at this special location, and now we see that they've been wiped out. Thus, the bootloader, when it's programmed these secret keys, gives me the capability to read them out if I need to for whatever purposes. However, it's only a single possibility because once the board is power cycled, they've gone. Here I'm showing 2 directories on my computer. The first one is the object image that I loaded. And the second one is the simulation directory in the uTasker serial loader. In this directory we find 2 files of interest. We find a file called atxp xxx.ini and i.MX_otp.ini. These are images of the flash memory and also the one-time programmable memory. I'm going to delete the one-time programmable memory, so we start with a fresh chip. And what I'm going to do here is I'm going to take a copy of this complete image which we loaded to our board and put it into this directory. Also, I'm going to rename it and delete the original flash image. So what I've now done is I've got our complete MicroTasker bootloader and application image in this file here. The next thing I do is I open up the MicroTasker serial bootloader in Visual Studio. Now when this runs, it'll read in the one-time programmable image and also the entire flash image. And we can see exactly what it does with it. Now the first thing that it does of interest is to see whether the keys have already been encrypted or not. What it's doing is it's looking at the one-time programmable lock to see whether it's been locked. If it hasn't, it will look at the keys which have been programmed. Here it finds that they are all zeros, which means it's never been programmed before. So it initializes the random number generator. Now what I've done at this point is that when I simulate, I'm going to use the exact same keys which we read back from the hardware. So what I'm doing here is I'm programming the exact same keys which are on the hardware into my random number, and then we call the function to save these to the one-time programmable memory. It checks to see that the save worked correctly, which it did, and now it sets the lock bits. It locks to the keys from being read back, and also it makes some unchangeable. So the next thing that it does is look to see whether the keys in memory have already been encrypted using this secret key or not. It finds initially that they haven't been encrypted. So what it does in this case, as explained in other videos and documents, is it generates its own key using the on-the-fly encryption across the bootloader memory range itself. And it uses this new key to AES-256 encrypted the original keys. It now saves these new keys into the flash memory, and it resets the original keys in the flash memory so that they no longer exist anywhere which are readable. Once it's done this, it'll reset. Moving back to the hard drive, we can see two files which were generated when the simulation closed. So if I open up the original file and I open up the memory file as it was saved by the serial loader, we're going to find a couple of interesting things. The first point of interest is that the original secret keys which were stored in the QSBI memory have now been completely deleted. However, some originally empty memory has now been used to save an encrypted version of this key. Going back to our hardware, let's see what happened there. And what you notice is that the simulation has been able to produce exactly the same result. So now we move back to our hard drive and I make a copy of these two files. And I paste them into the simulation directory of the MicroTasker application. And I allow the MicroTasker project to run in Visual Studio. The MicroTasker project also has an output terminal which I'll position here. And at the right hand side of the screen I'll position my hardware terminal. And let's do some comparisons. This is a view of my start of memory. In the simulation, of course I get the same results because it's using an image of the original file. But now we're going to move into the administration menu and we're going to use a command called secure on the fly test. Now what this command has done has enabled the secure on the fly decryption of a block of memory starting at this address. I have first to move to the I/O menu. So what we can see here is that we have the real content in the flash being read and compared with the on-the-fly decrypted version of it. Now I can do exactly the same thing here in the simulation. And what we see is we get exactly the same results. Now the reason why how the simulation can do this is because it emulates the way that the BEE or the OTFAD works, and it also uses the exact same values which are stored in the OTP. Of course, on the hardware here we could not read these. So let's check again. Looking at the eFuses, they're not valid. If I do this in the simulation, again we get the exact same behavior. They are not valid. However, the simulation does know what they are because the simulation has them in its OTP file. So I've stopped the MicroTasker application simulation, and I'm going to take these two files again, and this time I'm going to copy them into the bootloader simulation directory, and then we can see how the bare minimum bootloader reacts to them. So what it's doing here is seeing whether we have a valid application to run. The check of the content is positive. It recognizes that it's encrypted memory, which should be copied to the internal instruction RAM where it will then operate. It configures the flex RAM accordingly to the size, and then it does the copy. However, because it's an encrypted copy, it also has to retrieve this key. This is the key retrieval. Once it's decoded its AES-256 encryption keys, it sets them up for the AES-256 encryption process over this code. So here we can see the encryption process of a block of memory taking place. Here we copy a block of memory to be decrypted. So I've put this buffer in the memory display at the bottom of the screen, and now we're going to execute its decryption. Here we can see that it's been decrypted, and if I look at it in 4-byte format, we can see that it's valid because we have a valid stack pointer address and we have a valid start address in the internal program memory. Finally, we jump to this new application. Although it wasn't possible to show every line of code involved during this verification, the important principles are: the MicroTasker simulator simulates the complete operation involved, which means that every line of code can really be tested exactly. In order to be able to simulate the exact case for a certain chip, I did in fact have to plug into the simulation the values of this random number which is being used as the decryption key. Also, I made a reference of the unique silicon number in this device. So what I've in fact done with all of my reference boards, which have their random number programmed to them and are no longer accessible, so I use a technique which I showed to make a reference backup of each of these values. This means that I am in a position to simulate each of the boards' behavior in any circumstances. Normally, for boards programmed in production, the actual random number which is programmed in each of them is not of real interest. So I hope that gives a good overview of the simulation techniques available and how powerful they can be. It's also worth noting that the concept being used doesn't require any management of the secret keys. The secret keys are in the program. They are protected by the concept. The only fuses that need to be programmed are the ones which store this random number and the ones that protect this random number. In the future, I can reuse this board with other software using completely different AES-256 keys. Many thanks for watching this video, and good luck with the MicroTasker bootloader concept on your embedded artist boards.